Okay, so power functions, I forgot to write the fact that my example was not, so only one term. So x squared plus 5 is not a power function because it has two terms. Okay, so the plus 5 makes it something else, quadratic. Okay, here were examples of power functions then. So the degree here comes from here, the 1 comes from this, right? So clearly a 2, a 3, and then 4. So what do we know about the graphs of these functions from looking at the degree? So what does the degree tell us? And what does the leading coefficient tell us? Okay. So the degree 1, well, it tells us several things actually, but a first degree function could have how many solutions? Okay, so it could have one solution, a maximum number of solutions. And then the 3 for this one tells us that it is what? An increasing or decreasing? Increasing. Okay? In case you're wondering, this would be the graph of it, right? See how it has one solution? Yeah? So the second example, degree 2. Maximum solutions is 2. The negative 5 makes it decreasing. So it's going to go down on the right side. So degree 3, the maximum solutions is, could have had 3. 8 makes it go up. So increasing and up, we call the same thing. And I'm out of room a little bit, but this 4, so that's the maximum number of solutions. And then the negative 5 makes it go down. We okay on this? So in general? Now power functions are slightly different than some other polynomials in the sense that they only have one term, and it means that their graphs are very specific and they're easy to graph and easy to sketch. So I'm going to graph several of these. Well, actually, I graphed a bunch of these over here. So here's the, and a little bit hard to see, and I tried to space it. So f of x is x squared. That's the one right here. That's the one in blue. Over here, k of x is x to the 4th. It's a little hard to see maybe because this green line here is in the way, but it's this one and this one. So it goes up on both sides. And then we have a 2x cubed, which is the red one. And then we have a 6x to the 5th, which is this greenish one, or blue. I can't remember what color I picked for there. Okay? Yes. I'll put little arrows on them. This one's actually smack on the line. This one's the black one. So what kind of things do you guys notice about all these graphs? And you can split them in even degrees and odd degrees. Well, they're all power functions, so yes.
The odd exponents go down.
Yeah, and they go down on the left and up on the right. Yeah? Okay, that's called end behavior. How about the even ones? What do?
They just go up.
Okay, and that's their end behavior. The end behavior. So end behavior actually is a term that's well thought out. It's asking you this, is what happens, and then I could say at the end of the graphs, and I'm just going to rephrase it a little bit and say what happens far right and far left. So it's a question. Okay, so what happens? So far right, think of the furthest right on the x-axis that you can be. What is far right? Far right would be represented with what? Yes. And far left is negative infinity. That depends on the leading coefficient. So you're ahead of me. Just give me a second. I'll get to that. So far so good? So far right we represent with infinity, far left you represent with a negative infinity. Alright. So even degree. So things you should know about even degrees is, one, they have the same end behavior. In this case, when x goes to infinity, the function goes, and you would write it this way, the function goes what? Up. And what's the biggest number that you can think of going up? Okay, so it goes to infinity. When the function goes to a negative infinity, when the x goes to negative infinity, so when I'm on the far left, where does your function still go? Still up. Okay? Because if you think about this, where is this going to lead? At some point this is going to go to infinity, and at some point this graph is going to reach infinity. Yes? Alright. So that's always that is true for all even functions. So if the degree is even, it's always going to go up on the right and always going to go up on the left as long as the leading coefficient is positive. So how about here for odd degrees? What about the end behavior? When it's on the right it goes up, but when it's on the left it goes. Okay, so since odd starts with an O, I'm going to call it opposite end behavior. And so when I ask you to describe end behavior, I'm looking for this. That's how you're describing end behavior. So describe end behavior, when I say, or list end behavior, I'm looking for that kind of a notation. So here, when x goes to positive infinity, what does the function do? The function is still going positive infinity. When x goes to a negative infinity, the function is also going to a negative infinity. Opposite directions. Okay, we should be able to finish that sentence. Whether the function goes up or down on the right, so I'm asking you, is it increasing or decreasing? What does that depend on? The leading coefficients, yes. So sometimes we say leading degree. So it's the number that's with the leading, it's the leading coefficients tied to the largest exponent. But what do you notice about all the coefficients that I gave you here? They are all what? They're all positive. So this is why they all end up going up on the right. Because Ursula asked this, will even degrees always go up? No, that depends on your leading coefficient, which we saw in 6.1. Because we had functions that went up, and we showed functions that went down. And all I have to change is a negative, right? So is it possible for a function to go, for its end behavior to go to negative infinity and negative infinity? Yeah. You just need to make it a negative. What I mean with that is this. So the answer here would be, somebody said leading coefficient. So it depends on the leading coefficient. So this is why you needed to know some of these terms, so that hopefully this isn't completely strange for you. So I'm going to make a small graph here. Could this be a negative x squared? If yes, no, with other stuff, obviously. Okay, so yeah, it could be a negative x squared, and since I don't have it right at 0, 0, I would have to either plus or minus, so there's more stuff here, okay? What about its end behavior? Okay, well, so when x goes to infinity, the function goes to negative infinity. When x goes to a negative infinity, the function goes to negative infinity. See how the end behavior is the same? but it's no longer going to infinity. But that has nothing to do with even or odd. That comes from the number that's tied to that degree. So that's why I don't want you to, that you should not tie those two concepts together. Okay? Going even degrees, same end behavior, odd degrees, opposite end behavior. That's what you need to learn. Okay?
Can you go back to
Yes? Okay, so here are a bunch of things that you ought to now know about power functions, whether they're even or odd. And actually this applies to all polynomial functions, even or odd. And I'll get to this here in just a second. But so if it's even, you should have symmetry, right? Like x squared is symmetric. Yes? Yes? No?
Yes.
Okay. Well, if it's odd, it's origin symmetry. It runs this way. Yeah? I'm sorry, this way. Come back. The domain is the set of all real numbers. The domain is the set of all real numbers. The range for evens is going to be limited. Think about the picture of x squared. You don't have to memorize anything new for x to the 4th, or x to the 6th, or x to the 8th. What does x squared look like? It looks like this. So the range means it starts somewhere and it goes up, or it starts somewhere and then it goes down. Well, an odd function goes from positive to negative infinity. Why is that? That's end behavior. Think about that. End behavior, even degree is always the same, right? So the function starts somewhere and then it always goes somewhere. Yeah, always either up on both sides, right, sort of like a vertex, or down on both sides. So that's why it starts end behavior. What about odds? Well, they always do this. It has to. They either do this, go up here and down here, or you switch the coefficient and it'll be the other way. Right? This would be a positive function. And you guys, right? Up on the right, down on the left. Here's a negative coefficient. It's switched. So this range goes all the way through. If it's a power function, that's always true. 0, 0, 1, 1, negative 1, 1 is on. Okay? If it's a power function and it's odd, it's 0, 0, 1, 1, and then negative 1, negative 1, because you have near to the origin. But I'll spend some more time on that one. And then the last part, it's not that important. Sort of hard to show, although you could see it in the picture. It's a little hard to illustrate. So the first three I think you ought to be familiar with. So let's look at how can we use this then to graph polynomials, because I'm not just interested in power functions. We actually want to get this to polynomials, although I should add. All right. Let's first ignore this +2 part. Let's just graph an x to the 5th. Basically, I'm going to use translations here. So what would x to the 5th look like? What is its end behavior? When x goes to infinity, the function is going to go to infinity because it's positive. When x goes to a negative infinity, the function is going to go to negative infinity. Okay. So if I were to graph just x to the 5th, what would it look like? Well, x to the 5th goes to 0, 0, right? Yeah? And then it goes to the 1, 1. But then if you put the negative 1 in, it goes to a negative 1, negative 1. And this is what I said earlier. I'll get back to that. This is what was in that table. Now, I don't care if it's an x to the 5th, 7th, 9th, 11th, 13th, 3, whatever. The wiggle is basically the same. The amount of wiggle changes a little bit, but the wiggle happens this way. That happens with all power functions. Okay, that's what an odd power function, that's how it wiggles. So this could be the picture of an x cubed. If I grabbed an x cubed, it would be exactly the same picture. If it was an x to the 9th, it would be exactly the same picture. Okay, now let's go back, and I'm going to erase the +5. So I actually needed a graph, or the +2. So how do you change this into a +2? What does the +2 do to the function? Makes it go up how much? Yeah, just up 2, right? So I used to be at 0, 0. I need to go up 1, 2. I used to be at 1, so plus 2 is 1, 2, and this one goes up 2 as well. So here is my best guess at what this function looks like. That is x to the 5th plus 2. So how many accurate points did I graph? Okay, so you should be able to graph 3 accurate points, and I have my end behavior listed. And that's how you graph a power function, or that's how you graph a polynomial based on a power function, because x to the 5th plus 2 is not really a power function, right? Okay. So sort of the same thing here, and I can't erase all this mess. So let's just look at what does x to the 4th look like, and see, I'll do the basic function in red. So what does x to the 4th look like? So ignore all the other stuff. What does x to the 4th look like? What is its end behavior is? Yeah. Alright, so let's list that. Okay. So let me graph that. So in red is the original function, or the parent, we call that a parent function, right? You've used that term before? Okay, so x to the 4th would go through 0, 0, it would go through 1, 1, and then on the negative side it would also go through 1, right? That's what makes it go up. Okay, so, well, that looks a whole lot like what? That looks like x squared. And if I don't make any more markings, it is pretty much your guess as to which one it is. Okay, so you'd have to have the function. So these are called sketches because it's sort of hard to distinguish between an x4, an x6, x2. Yes?
Wouldn't you have to move one more time?
No. Why?
Not if we're just graphing x4.
So if you're thinking an x to the 4th could have 4 solutions, you're okay with that, right? But to make it have 4 solutions, I would have to have a whole bunch more junk with it. Does that make sense? Like it would have to be an x to the 4th minus an x cubed plus 7x squared minus x plus 10. And I just graphed an x to the 4th. Is that okay, Ashton? Okay. Alright, now let's see what does all the stuff do. So in blue, we're going to graph the transformations. And I probably should list them, and I should have listed them over there. Well, I did list them, sorry. Okay, so what are the transformations? Nope. The leading coefficient is going to be -2 here, yes. So the -2 is still your leading coefficient. So that gives me 2 things actually. So that is your leading coefficient. But I don't want to start with that one. I want to start with the +1. What does the +1 do? Which way? Move. Move left. Okay, so the +1, and we'll circle this, actually moves left 1. Yeah? And then what does the -2 do?
It makes it go down instead of up.
Right? So we call that a flip, right?
It makes it go down twice as fast.
Twice as fast. So the other thing that you can say there is multiply your y's by 2.
So it would be
So
1, 2, 1.
yeah. Except we're going to move it to the left, right? I mean, we're going to move it to the left. Is that correct?
Yeah.
All right, so we're here, I'm here, and I'm here. I moved it left 1. Then we're going to flip it. So now it's flipped. So we're here and here. When you flip this on the axis, it stays. And then here's where the 2 comes into play. So this used to be a jump of 1. The 2 is going to make this jump 2. Here's the 2. Okay, this is what the -2 does. It makes it go from, instead of just going from here to here, we're going to go from here to there. And then here's your graph. How many accurate dots do I have? 3. 3 accurate dots. Based on transformations. So 3 accurate points. Okay?